Okay, welcome to the 5th rotation video, and we're going to be looking at how conservation of energy applies in rotation. Now, as always, we're going to do this by considering the analogy with the linear variables. And the first thing we need to do is to define work. So the first thing is, in linear variables, work is force applied through a distance. So F delta x cosine theta, or to use vector notation, F dot delta x. And if we have a variable work, or variable force, the work is the integral of F dx. So using the rotational analogs, we'll say that work is a torque, is torque applied through an angle. And I messed up there. That should be, oh wait, yeah, cosine theta. Never mind. Where in this case, theta is the angle between F and delta x. And in this one, theta means something different. If we've got some object that rotates through an angle theta under the influence of a torque. And if we have a variable torque, which is something you're not going to see a whole lot, but if you have variable torque, the work done by the torque will be the integral of torque d theta. Now, since theta isn't really a vector, there's no dot product here. And now we can also find an expression for power in rotating systems. So remember, the definition of power is the rate of doing work, which we said was force times velocity in linear variables. Well, in rotation variables, it's going to be torque times angular speed is the rate of doing work. So really, nothing too terribly complicated there. So now let's see how we use conservation of energy. Well, it turns out that conservation of energy works exactly the same way it did before. It's still going to apply in systems where you have no friction or other non-conservative forces. The difference is that we'll have our potential energy, we'll have our kinetic energy, but we'll actually have two kinetic energy terms. One for linear motion, translation of the center of mass, and one for rotational motion. So let's consider this problem. You've got, the idea here is that you have a spherical shell of radius r and mass m, and around that is wrapped a string, which then runs over a pulley and goes to a weight of mass m. No friction, frictionless bearings means we can use conservation of energy. The cord is massless, that makes it easier. This pulley is massless too, which also makes it easier. And then we want to find how fast this is going after the mass has fallen through a distance h. Well, there's two ways to do it. First off, we could use torque. We can set up Newton's second law for rotation. We can find out what the acceleration of the system is, like we did in the previous video, and then use a kinematic to find the distance or find how fast it's going after h. But it's a little bit easier to use energy. So let's say that we set the potential energy equal to 0 there. Now initially, we have our initial kinetic energy is 0 because nothing's moving, nothing's rotating. And our initial potential energy is mgh. Now our final potential energy has got to have two terms in it. There's the there's the translational kinetic energy of the weight, which is 1/2 mv squared, and there's the rotational kinetic energy of the spherical shell, 1/2 I omega squared. And then the final potential energy will be 0. Now, since we're using conservation of energy, the total initial energy equals the total final energy, and we have mgh equals 1/2 mv squared plus 1/2 I omega squared. But the problem is that we know that omega here is related to v. The larger v is, the larger omega is. Not surprisingly, v equals, or rather, omega equals v over r. And now the other thing is, the moment of inertia of a hollow sphere, that's one of those shapes that where we have a formula for the moment of inertia, and it so happens that it's 2/3 mr squared. And so we'll end up with mgh equals 1/2 mv squared, and with a little bit of algebra, we get 1/3 big M v squared. A bit more algebra gives us v equals the square root of mgh divided by 1/3 m plus 1/2 little m. You should work through all the steps out, make sure you get the algebra. And there we go. That was easier than using Newton's second law, wasn't it? And I believe I was intending to use this slide to work the same thing using Newton's second law, but I don't think I'm going to. Instead, I'm going to end with saying that your equation, or the problems I'm going to be checking tomorrow, is just problem 61, part A, but I'd also like to see you set up part B of the problem. Don't solve part B, but at least set it up.